Hey, everybody. I have a bit of a cold today, so I'm going to use the mic. Can everybody hear me okay, though? Okay, great. Today is an exciting day in terms of this class, in my opinion, because we get to start talking about Mars, which is a very, very intriguing planet. I'm seeing some cheers in the audience. That's good. I like that enthusiasm. Mars is cool enough. We're actually going to devote more than one lecture to it. So today we're going to be discussing explorations that we've done of Mars. We're going to discuss the atmosphere and the geology, some important features on the surface of Mars. But I think a lot of people are very intrigued by Mars because of potential for water and life on the planet. We're going to save that for Friday. So I figured that was a more fun Friday afternoon kind of lecture. So don't forget to tune in next week, next class. Um, to start off, I think Mars is also fun because it's a good planet to speculate about a lot of different things. One of the things that we like to speculate about is Mars is definitely the most likely planet that we would ever travel to as humans. Mars is the most likely place we're ever going to travel to as humans. But there's a lot of caveats to it. It's very far away. It's much further than the moon. It took like 3 days to travel to the moon. It takes 1 year at best to go to Mars. If you're on Mars, it's also very, very hard to come back. That fuel is very expensive that you need to launch off that surface. So at best case, you're looking at a 3-year trip if you signed up as an astronaut to go to Mars. So 1 year there, 1 year on the surface because of the way the orbits are, 1 year back. But a lot of people even argue that it might make more sense to have a one-way ticket to Mars and then just never come back for the astronauts. So as I said, today we're going to talk about Mars, key characteristics, surface features, atmospheric evolution, Martian moons, and we will have an activity at the end of the class. So key characteristics of Mars. So Mars is named after the Roman god, sorry, a god of war. The reason probably is if you see it in the sky, it has a reddish color, and the planet is, of course, very red. And the reason for that is there's a lot of iron oxide, which is the fancy scientific name for rust on the surface of Mars. Basically, Mars is a giant rusty planet. The second reason it's probably a good god of war, beyond the fact that, it's blood colored in the sky, is it can actually vary very dramatically in brightness depending on where it is in our orbit compared to Earth. So this is a really nice series of astrophotography I found, which is by an amateur astronomer, just showing how Mars, he in 2020, it was the pandemic, he had time to do this. From the 3rd of March until the 26th of September, which was the closest approach of Mars that year, you can see that it's, it gets an order of magnitude brighter, basically, because you just have so much more of it, so much closer. So there's a lot of the time that Mars is visible in our sky, but it doesn't really look much. And then it will suddenly become, not really suddenly, but for a few months, it will become very bright. So, for the real Harry Potter fans out there, there's like the centaur looks up and is just like, Mars is bright tonight. That's not actually completely enigmatic. It's actually, sometimes it is very, very bright. I could totally believe if you think astrology is real or something in the ancient times where they didn't understand planets and how they move, everything like that, like we do today, you would be like, yeah, this is probably a sign that something bad is going to happen. I did look it up. Unfortunately, Mars is really, really hard to see right now. It's about to go into the sun at sunset. It's going to come back next year, so look it up. And then the next one of these oppositions, so closest approaches, is February 27. It's going to be at this very bright period again. It's about 2 years for Mars to go through a cycle on Earth for our visibility of it. The planet itself is not actually that big. Mars is about half the size of Earth. Its mass is significantly less than that of Earth. Its density is also significantly less. Orbital period, it's about 1.5 times our distance from the sun. So it takes 687 days to go around the sun. The rotation period, it's not quite 24 hours, but it's pretty close. So it's like an hour and change, or 24 hours and change. A Martian day actually has its own name. It's called a SOL, S-O-L. And that's basically important if you start going into Mars missions and like researching them, then you'll see like durations in sols instead of duration in days because, well, on Mars, wouldn't you measure time in sols? Orbital tilt is also pretty similar to Earth. It has no real magnetosphere and things like that, but it's a comparable as well for that. So Mars does have seasons. They're just, as we're going to discuss, a little different than our own. So missions to Mars. So Humans, basically, since we started doing space launches, have been sending a lot of probes to Mars. Mars is, however, very difficult to get to. And about 60% of all probes that have ever been sent to Mars have failed. So this graphic, I know you can't see the details, but you can get the general gist. This line here is if a mission failed. And look at how many on this line did not actually make it to Mars. They failed in some capacity, especially at the beginning. It was very hard. We didn't really know how space rockets should go, things like that. You just had a lot of failures going to the planet. They didn't really succeed. Then there's some more embarrassing ones along the way. My opinion, the most infamous American failure is one called Mars Climate Explorer, which was in 1998. It was supposed to be like a satellite going around Mars to measure a lot of stuff about the atmosphere. There was a mistake made in the code between NASA and its contractor, Lockheed Martin, where Lockheed Martin had some of the values in imperial units, so like what we use, instead of the metric system. Sure, everybody knows that scientists, we always use the metric system by default. This ended up actually burning up the atmospheric probe, and it was a $700 million mission, just poof. And that was really, really embarrassing. They double check these things now for sure. But yeah, so there's some failures that are like, oh, the rocket blew up, some failures that are more embarrassing. The point is, it's been traditionally very hard to go to Mars. I actually had a friend in college, her car was named Mars because it was red, rusty, and a 2/3 failure rate. But that's kind of what we're dealing with here. I will finally note, though, on this graphic, so this is chronologically, we started in 1960s, go to here to present day. You'll see we're getting a lot better at going to Mars now. And that's somewhat the technology is getting better, experience, things like that. But it's still always a little dicey when one goes, everybody gets really nervous. So the Soviets had the first attempt, Mars 2 in about 1971. One landed for like 20 seconds and then copped out, so it wasn't really considered very successful. The first successful mission landing on Mars was Viking 1 and Viking 2, which were in the United States, landed in 1976. So the first landing was very exciting. They also had a test where they dug into the soil and tried to test the soil to see if there were any signs of life in it. It was unsuccessful. We're now thinking that that test might have been inconclusive. I'll tell you guys more about that on Friday. They lasted until about 1982. Then they accidentally sent a wrong code from Earth to the probe. The antenna pointed the wrong way and they could never contact it again. Yeah, Mars is hard, guys. But then we didn't really go to Mars until 1997. The Sojourner probe, which is this little guy up here, worked for 85 sols. As I said, a sol is basically a Martian day. And it was kind of a proof of concept of, could we send a rover to Mars? So these days, Mars rovers are a dime a dozen. There's actually more than one currently working on the surface, but nobody really knew if this was possible to do on another planet. Sojourner was the first one to really kind of test that out. And then it was successful. They went around, they looked at rocks. They also had the first time for landing on Mars, because how do you land? We'll discuss the atmosphere is only about 1% that of Earth's. So doing parachutes and stuff was actually pretty hard. So they ended up having like a giant ball of balloons and it bounced around on the surface. And then that's how it settled and wasn't damaged. And then 2003 was really kind of the big year, 2004. So they sent two probes called Spirit and Opportunity. And those were the first real probes that were actually doing proper science on the surface of Mars. The other thing that's amazing about them is they were engineered to last 90 days, and they ended up lasting, as you can see, 7 years or well over a decade in the case of Opportunity. So these little rovers were really successful as well, beyond anybody's best dreams. The reason, by the way, is first of all, you always engineer. Anybody who knows engineers, they always underestimate how long something can last. If you're building something, you don't want to overpromise. The second reason is there were some assumptions that eventually there's a lot of dust on Mars, and the dust would go on the solar panels. So the solar panels that power the things are back here. And then eventually you would have dust landing on this solar panel, so you wouldn't be able to run it anymore. Turns out there's enough Martian wind that the dust would just kind of blow away. So that was actually just very lucky. And these guys lasted pretty long. In 2012, still running, Curiosity was sent, which is the next generation of these rovers. To show you why I'm saying the next generation, I'm actually just going to show you guys these three rovers in particular in scale. So this is Sojourner. You can see it's kind of like your model car, maybe a little bigger, something like that. Spirit and Opportunity were this size, so definitely, order of magnitude bigger. By the time you get to Curiosity and Perseverance, which is the other most recent rover, they're basically the size of your car, like a car. Yeah. We'll talk about that in a minute. Yeah. So the Mars rovers have become really amazing. They have a really long endurance life. They're designed to last for years, basically by now, on the surface of Mars. I should also point out the reason that you have this picture is they build these at JPL, Jet Propulsion Laboratory in California. And they basically will always have an extra one that they keep in JPL. So then they can test it and understand stuff before they send commands and things like that. So they can test these rovers and understand what the Mars ones are doing versus the ones there. I also did visit JPL once. They were building, I think, Curiosity at the time. And there was totally somebody in the parking lot whose bumper sticker said, "My other car is on Mars." So yeah. We also tend to anthropomorphize them. So this was the day Spirit died, this comic came out where it's little Spirit, the first day of his 90 missions. 89 days to go, 2 days till I go home. Day 91, what happened? Maybe I didn't do a good enough job. Maybe if I do a good enough job, they'll let me come home. I thought I analyzed that rock really well. It's okay, I'll do the next one better. Day 1328 of 90, sandstorm, power dying. But a good rover would keep going, a good rover like they wanted. Oh no, I'm stuck. Did I do a good job? Do I get to come home? Guys? And there it is, all alone on the planet Mars. And if you don't feel bad enough already, this is actually true. I'm not making this up. They made Curiosity on the 4th year of its mission sing happy birthday to itself on the planet with nobody else to hear it. So this is actually a genre of people taking these rovers, very anthropomorphizing. A lot of people really love these guys. So Curiosity here. I didn't have room on that slide. So Perseverance is the most recent one, 2021, still kicking. Perseverance was cool because it also had a little helicopter called Ingenuity, which lasted for 3 years. And that was the first time you actually had another, a little helicopter, automated flights on another planet, thanks to that helicopter. Some of it was to test just how do you fly around in the atmosphere of Mars. It did a little bit of basic science as well. I should point out also Curiosity and Perseverance. They're also big enough rovers that you can no longer just have a bunch of balloon balls and have it bounce around on them. They actually had a sky crane. So it's a rocket-powered crane. And this all has to be automatic. It's 7 light minutes at the best to Mars. So by the time anything goes wrong, it's too late. Lowered this thing and then flew off. So the engineering here is really exceptional. And we also should mention that the Chinese had their first rover landing in 2021. It lasted till 22. So they said 90 sol mission. It lasted more than that. It's closer to a year. And currently the next one is actually a European rover. It's currently being built. They're targeting 2028. You basically, every 2 years, you have a really good launch window to go to Mars. So that's why it's 2028 is the next really good one in terms of, if you're not making next year. And then the next kind of phase, because, okay, we have these rovers, they're looking at all these rocks, that's really cool, is actually something called Mars Sample Return. So both the Chinese and the United States plus Europe, it's a joint mission for the USA and the European Space Agency, are trying to basically go to Mars, get some rocks, and bring them back to Earth. Because especially when you're trying to find life, and we'll discuss this more on Friday, it's pretty difficult to definitively say, even if you have a robot and you can do everything versus bring something into a lab, do tests in a lab, Mars rocks would be a very high commodity item. Let's put it that way. The United States one is currently in a bit of a boondoggle. I hate to say this, but they keep pushing the date backward. It was 2030 was the original idea for the launch. The most recent thing was maybe 2040, and also the cost is going to be $11 billion. Let's put it this way, NASA, even before this current administration, was we're going to have to rethink that one. That does not sound very realistic. The science budget for NASA, that would be a giant fraction, and NASA could then basically not do much else in science if we end up funding the Mars Sample Return for $11 billion. I also think, honestly, in this current administration, with the current funding priorities, that's just not going to happen. The Chinese, though, are a little more optimistic. They're still targeting a launch in 2028. And then a return in 2031 of their rock samples. So we'll see if that ends up happening. But yeah, so the idea is you have your rover that would go around and collect the samples. Perseverance has actually collected samples in little tubes and has left them behind for something to then pick up. Maybe like an Ingenuity helicopter could go pick them up, put them in the main thing, and then launch them is kind of the dream there. Yeah, and then eventually you would launch back, bring those samples back to Earth. We'll see if it ends up happening. It's much, much harder, as I said, a one-way ticket versus bringing something back. Yes. We do, they're meteorites. Yeah, so we have meteorites, and we'll discuss this more on Friday, that we have identified that they're from Mars, and that's basically because we can measure the chemistry of Mars very well because we have all these rovers there. Then if you find a meteorite, you can see that its composition is comparable to Mars. But yeah, so this is kind of the rover overview. And the thing that I really want to emphasize is it's really amazing. Like you can just see Mars now. Like you can go on the internet and like explore it as much as like some of these rovers have gone several miles by now. So you see all these vistas. So this is one, just Perseverance, looking toward a hill called Santa Cruz in 2021. And I thought this was a pretty cool image when I was preparing this lecture. This was taken by Curiosity in September 2015. I'm just curious, does this look familiar to anybody? Does this remind you of somewhere that maybe you've been? Okay, I'm not saying you've been to Mars, but I'm saying like I've been to Utah, for example, and I feel this really looks like sandstone desert or something like that on Earth. Like it's very, very comparable in my opinion. Final thing, you can even like see videos of dust devils going around. So this was taken, it was a 4-minute observation of a dust devil going around on Mars, which is kind of amazing. And if you really want to get into looking at more Mars stuff, we can actually do that. So the data from the rovers is actually put up pretty much immediately on the internet. Like there's the raw image. This is of the week. You can see what was taken, or the latest one. So this is a raw image that was taken, today, earlier today on Mars, beamed to us, picked up, and that's what Mars looks like today. So I think that's just, one of the neatest things that we've actually gotten to the point of space exploration where we actually just have eyes on other planets and can see what everything looks like out there. So moving on, Mars has 2 moons, Phobos and Deimos. So Phobos is a small rock compared to our moon. It is 7 million times less massive, takes 7.5 hours to orbit Mars. So it's pretty close. In fact, it's actually going slightly closer to Mars with every single one of its orbits. And it's thought that it will crash into Mars someday, maybe like 50 million years from now. So not on our timescales, but on a solar system timescale, that's relatively soon. The second moon is called Deimos, which is 49 million less time. So even smaller than the moon. And it takes 30 hours to orbit Mars. Phobos and Deimos are named Fear and Panic, which are basically associated with the god of war in literature. But I'm giving you these sizes like much less than, I know we have no real perspective on this. So just to show you guys, if we took Phobos and placed it on top of Eugene, that's how big it would be. So pretty small rock. It's basically a Eugene-sized rock. And then if we did Deimos, it's even smaller. So these are very tiny moons when we're thinking in comparison to our own moon is the real answer here. Here's a question, make sure people are paying attention. Deimos takes about 4 times as long to orbit Mars compared to Phobos. Which one is further from Mars? Phobos, Deimos, same distance, or you can't say? Trying to figure out what that one is. B, okay. Most people just do 2 fingers, but yes, so B. Deimos is further out, much further out. It's actually much more difficult even from the surface of Mars to see. Like you could see it, but it's tough because it's also fairly dark. I thought this was cool. Yeah, we have eyes on Mars, right? What should you do with them? We can watch an eclipse on the surface of Mars from the Perseverance rover. So, and just to give you an idea, like I think I told you guys eclipses, the fact that our moon does it so perfectly in front of our sun is actually a very unusual thing. Now you kind of get an idea of why, because like, okay, you have this space rock looming kind of above you, and this is the best it can do, covering the sun. So It's a pretty unusual circumstance that we get the eclipses we do on our own planet, but also just gives you, I think, a sense of scale of how these things are not that big. Okay, so Phobos and Deimos, a lot of people have said over the years that they're probably just captured asteroids because Mars is very close to the asteroid belt. Recently, there have been some studies that have come out suggesting that it could have been some sort of progenitor, so some bigger space rock that disintegrated when it came too close to Mars. It's called the sister hypothesis because, well, there's two left. The idea is that it's very difficult that in the orbits that they're in, they're very equatorial orbits, very nice orbits, to be just random captured asteroids to get those orbital dynamics exactly. There's also problems, though, suggesting that maybe this was something that disintegrated, because then you should have some sort of ring. Like you should have smaller pieces of stuff left over around Mars. We definitely don't see that. So the jury's a bit out on this. There's actually going to be a mission the Japanese are sending to Phobos to look at the rock, things like that. So hopefully that would tell us if it's rock similar to asteroids or similar to something else, and maybe that'll answer the question someday. Surface of Mars. So the true color surface of Mars, I wanted a globe, but it didn't show up today, unfortunately, but you get the idea here. It's red and rusty. You have some polar caps at the top and a little bit at the bottom as well. And then we have a couple major features, which we're going to discuss in detail. The Hellas Basin, Valles Marineris, and the Tharsis Bulge are kind of the three primary ones. We can also look, this is a false color surface. So the idea here is that the blue color is lower and then the red color is the highest. So you have the northern plains up here is kind of the other main one, the southern highlands, which are higher. But the point is there's also very much similarities to Mercury, Venus, and the moon, right? We have lava plains, we have highlands, we have craters. By now, you guys kind of know a few things about what these various features mean. Like this is, for example, much older. This looks pretty young, intriguing, blah, blah, blah. So to discuss these in a bit more detail, the Hellas Basin is the largest crater on Mars. To give an idea, it's basically just shy of the size of the United States. So very, very large impact when it occurred. And its depth is significantly large. It's 4.4 miles. So this is one of the largest craters that we know of in the inner solar system for sure. Probably more interesting, though, are those other features that I mentioned on Mars. So the first one to mention, this has something to do with Mars's tectonic history. Mars does not have plate tectonics like we do, but it definitely has evidence of volcanism and things like that occurring in its past. So the Tharsis Bulge is the biggest example of this. So this is basically a volcano-covered plateau on one side of Mars, which was lifted up by upwelling magma. And the most famous resident of this part of the planet is Olympus Mons. So Olympus Mons is the largest volcano and mountain in the entire solar system. So it's about 22 kilometers high, which is equivalent of 72,000 feet. Last erupted about 25 million years ago. So this is very, very big. It's hard to emphasize enough how big it is. So I found a couple graphics online. So here's an example of two famous mountains on Earth. So this is from sea level, not from like the base of the planet. But so Mauna Kea is a quite respectably high mountain. I think that's fair to say. One of the in Hawaii. Mount Everest is, of course, our tallest one. This is also in reference to the sheer size of these volcanoes or mountains on Earth. Olympus Mons, on the other hand, is just several times higher than either of these. It is absolutely ginormous. The other reason it's big is also just the sheer physical size of it. So this is if you superimpose Olympus Mons, which let's remember is just one giant mountain, onto France for a comparison. So it's basically, the size of a, European country. So it's absolutely, absolutely giant. The thing that's also crazy about it is it's a pretty low gradient. It's about 5%. So an astronaut could walk up with absolutely no trouble the entire way. This is not like climbing the Sisters or Mount Hood or one of our volcanoes on Earth. It's actually very gradual. It's also so big that there's nowhere on the surface of Mars you could actually see its entire size. because it's so big and Mars is, about half the size of our own planet. And if you're at the top of the mountain or near the top of Olympus Mons, you actually wouldn't even know that you're on a mountain. It would just kind of look like a low kind of edge coming up toward you, for lack of better explanation. So Olympus Mons is absolutely crazy. And here I'm going to see if you guys have any ideas. What do you think allowed Olympus Mons to be so tall? I gave you a few options, just seeing. Okay, I'm seeing a respectable difference of opinion. Let's put it that way. I'm seeing all the things. So I'm going to just tell you. The answer is gravity. The gravity is lower on Mars. So to explain what I mean by this, let's compare to Venus, Earth, and Mars. So the tallest mountain on Venus is Maxwell Montes, which is at 11 kilometers tall. The tallest Mauna Kea, this is from base of the ocean to the summit. Mauna Kea is actually taller than Everest if you went from ocean down at the bottom, measured up. And then Olympus Mons is 25 kilometers. If we then compare, so 10% taller, 2.5 times taller. The surface gravity, on the other hand, compared to Earth, is about 40% that on Mars compared to our own planet, and it's about 90% on Venus. So this effectively means that the surface gravity, 9% smaller, 2.5 times smaller. The volcanoes can just literally get bigger, because what happens on Earth, or the limiting factor on other planets as well, is eventually, so imagine Mauna Kea, you have lava, keeps bubbling up, keeps bubbling up. Eventually, it will actually have so much weight, the mountain will start sinking into the magma. And then eventually, someday after that, once it's no longer active, it will actually start to erode, of course. But actually, the limiting factor on how tall a mountain can get on Earth is the sheer weight of it and gravity. You don't often run into this, like Mount Everest is still growing. It can still grow for another 1,000 or 2 feet before this is going to kick in. But I'm just letting you guys know, like, this is why Olympus Mons exists and why we can't have a mountain so big on our own planet. The next feature, though, so it's right next to the volcano region on Mars. So these are the volcanoes here. You can see on this side of the image. And then we have Valles Marineris. So this is a canyon that effectively stretches from one side of Mars to the other. And it's 4,000 kilometers, or size of the United States, long. It's 200 kilometers wide, or 120 miles. So, distance from here to Portland or so. And it's 7 kilometers deep. It is, in fact, so deep that if you had a helicopter, so you took the little Martian rover helicopter and floated it into the center of this, you would see nothing around you. You wouldn't be able to see either side. You wouldn't see anything below you unless you were really, really lucky and the sun was maybe directly overhead. So this canyon absolutely dwarfs any equivalent thing on our own planet. So here's a question for you. How did Valles Marineris form? You have 4 options here. Okay, I'm seeing pretty good divergence, but actually a lot of people have it correct. It was actually ripped open by upwelling magma. So this is what this looks like on Earth. So think about it this way. Olympus Mons and the other Tharsis volcanoes, the reason they're so big is we don't have plate tectonics on Mars. So if you have magma that's coming out, it's basically just going to keep going the same place. So Mauna Kea, for example, in Hawaii, the plate moves, so eventually you get new volcanoes, right? So you have a certain amount of time that a volcano can exist until the plate tectonics shift everything enough that you're not going to have a volcano anymore there. That doesn't happen on Mars. You just have a constant kind of volcanic eruption that just went for, millions of years even. So what ends up happening, and I wish I had my globe, but oh well. So you kind of end up having a giant bulge on the side of the planet that's like kind of like a giant zit, basically, on the edge. And it's like a noticeable surface feature. As the planet is rotating, going through space, this really stresses the crust of the planet. What ends up happening is you get a giant rip, which is basically Valles Marineris. So it's basically a giant fracture in the crust. And then it's ripped open, and then the magma basically will also upwell. So it's the fact that it's so big, it has to do with the fact that it's next to the giant volcanoes next to it. And there was just so much stress on the entire planet that it ripped open this giant seam. So something that we don't really get on our own planet because of plate tectonics, but really, really astonishing, honestly. As a final note for tectonic history, there's no tectonic plates. but there is seismic activity caused by meteorite strikes and crustal stress in the planet. So we can actually see Mars quakes. They're very, very low level compared to our own planet. Mars also has no real intrinsic magnetic field like we do. It's probably because it's so small, it cooled down. You no longer have the liquid core required in order to have magnetic fields. So, atmosphere of Mars. This is a biggie. Mars has an escape velocity of 5 kilometers per second. I think you guys are used to this question by now. So which of these gases would be expected to escape off of the surface of Mars? Actually, I just realized, okay, you guys have 4 options and I put a 5th. I'll just tell you it's none of these. All of these are still present on the surface of Mars. So the atmosphere of Mars, primary, secondary, same story that we've seen already for other planets. They had the same still had the same primary and secondary atmospheres as Mars and Earth, but evolved a bit differently to the current atmosphere, and this has to do with Mars's size and its temperature. So what happened for these different things on Mars is in Venus, the secondary atmosphere disassociated because of that runaway greenhouse effect. On Earth, basically all that water became our liquid water in our oceans and everything else today. But you'll notice, so the reason it happened like this is because on Venus, we discussed Venus is very hot. The water could go higher, get ripped apart by the UV radiation. Earth is, lucky for us, pretty nice place to be. Mars, though, is pretty cold. If you're looking at the temperatures on Mars, it basically doesn't get above freezing, even on like a sunny day. Sometimes you'll get close, but it's a very, very cold planet because you're just further out. So the water is still there. We'll discuss more on Friday how we know this. There used to be quite a bit of water on Mars as well, but it's no longer in the atmosphere. It appears to be frozen, probably, in ice under the surface, primarily, things like that. Carbon dioxide is the majority of the atmosphere on Mars. It did survive, but a lot of it has also been absorbed into the surface rock or frozen on and under the surface. So the way this works is, we had the greenhouse effect. We've discussed this, the carbon cycle. So we have the incoming sunlight striking the surface. We have the infrared light leaving. Then we have the planet's temperature is kind of what determines the rate at which this happens. Water will condense, and CO2 in our own planet gets absorbed into that water. That does not happen on Mars. What ends up happening instead on Mars is you have the carbon dioxide. It did initially mix with some water when there was still liquid water on the surface. But then you have less of a greenhouse effect for heating the planet and the CO2 combined with rocks. So most of the CO2 that used to exist on Mars is now no longer in the planet, and the water is frozen below the surface of the planet. What this ultimately means is Mars also has a much smaller atmosphere in terms of if you're looking at Venus or Earth. Martian atmosphere is maybe 1% the mass of the molecules in it compared to our own atmosphere. We're going to skip that. So SO2, sulfur oxide. We do have some of it on Mars, but not too much. Most of it has been absorbed into clay through sulfuric acid. So acid rain was a thing that was present on Mars, does not really exist anymore. Acid rain happens on Venus too, but it basically never reaches the ground. It's in the upper levels of the atmosphere, so it doesn't really affect the sulfur dioxide later. The nitrogen has survived, well, some of it. The noble gases also survived. So what you basically have in the atmosphere is so carbon dioxide primarily and a little bit of trace amounts of these other gases. What you also have in the atmosphere is mostly clouds of frozen carbon dioxide, but sometimes you will have clouds made of water vapor and dust. The atmosphere is very thin, as I said, about 1% of that of Earth, but you can have fast winds and they'll still carry around dust. There's sand dunes on Mars. They don't significantly affect those sand dunes. And the dust storms will repeat every couple of years. So I have some videos of what this looks like. So this is another rover image showing clouds on Mars. And I don't know about you guys, but this looks like the clouds on our own planet. Actually, NASA thinks that these are not carbon dioxide clouds. They think these are actually water vapor clouds. They can also exist in the Martian atmosphere. But the point is, like, very thin atmosphere, but you can still have clouds. They're also about the same distance up from our own planet. So, different, maybe not that different. The dust storms, though, are definitely a problem, especially if you're thinking of future Mars colonization. So these dust storms repeat about every 3 years. It has to do with the Martian season. And these dust storms are so big that they can cover the entire planet. So this is May 28th to July 1st. So you can basically see that Mars, you still see features. And then by July, there's no features that you can actually see on the planet. It's just completely covered, completely enveloped. It can last weeks and weeks. Most of the Mars rovers so far that have failed, it's basically eventually you get a dust storm that is so big and so long that you run out of power and you can no longer contact the rover even after the dust storm has passed. And as I said, there's often very, very hard to escape these things because they just envelope the entire planet. So where do you go? So something to think about in the future.